And now we have Pascal's principle. Any change in the pressure applied to an enclosed, incompressible fluid is transmitted to any point in the fluid. This is referred to as Pascal's principle. For instance, say we have a fluid of volume density ρ1, a fluid inside a container. Let this be case 1. The pressure at depth H1, P case 1, we know this pressure to be equal to P naught plus ρ1 GH1, where P naught is the pressure at the surface of the fluid. We could look at this equation in terms of Pascal's principle. P naught is applied on this point of the fluid. In turn, it is applied at all points inside the fluid. It is applied here at this point, applied at this point, applied at this point, applied at this point. Therefore, at depth H1, P naught is also applied. If, say, we add another fluid into the container, a fluid, say, fluid 2, and fluid 2 does not mix with the first fluid, so fluid 2 simply floats on top of the first fluid. Let this be case 2. The pressure P naught will be applied at the surface of the second fluid of volume density ρ2. The second fluid has total depth of H2. P naught will be applied on the surface of the fluid of the second fluid. In turn, it is applied at all points inside the fluid. It is applied at the interface between the two fluids. In effect, we can say that P naught is also applied to the surface of the first fluid, just like in the first case. Therefore, the pressure P case 2 at the same level as in case 1, the pressure P case 2 is given by P case 2 is equal to P naught plus ρ1 GH1. ρ2 GH2, pressure due to the second fluid, is applied at the surface of the first fluid. So, Pascal's principle again, that pressure is applied at all points inside the first fluid. It's also applied at this point of depth H1 inside the first fluid. Therefore, we have plus ρ2 GH2 for P case 2. So, P case 2, because of Pascal's principle, P case 2 is now P naught plus ρ1 GH1 plus ρ2 GH2. Application of Pascal's principle. Any change in the pressure applied to an enclosed, incompressible fluid is transmitted to any point in the fluid. One application of Pascal's principle is in hydraulics. Put in simple terms, hydraulics involves applying force using fluids. Consider the following situation in static equilibrium. You have a container, and this container is filled with a fluid. The container is open at two ends. At this end, it has a cross-section area A1. The other end has a cross-section area A2. Let's say we have a piston at area A1. The same goes for area A2. We have a piston here. We use the piston to apply force. So we apply force on area A1. We apply force on area A2. Pressure is force applied on an area. Therefore, there is pressure at this location, the same goes for this location. So at area A1, we have pressure P1, and at area A2, we have pressure P2. Pascal's principle tells us that any change, any pressure applied to an enclosed, incompressible fluid is transmitted to any point in the fluid. So if, say, we start looking at this location, pressure P1 is applied on the fluid at this location, at this point. That pressure is transmitted to all points inside the fluid. So we can say P1 is also applied on area A2. So above the piston, we have pressure P2. Under the piston, we have pressure P1. Now, the system is in static equilibrium. The piston, for example, is in static equilibrium, which means the pressure above the piston is the same as the pressure under the piston. P2, P1, P1 is equal to P2. And since P is just force divided by area, P1 is equal to F1 divided by area A1, pressure at area A1, and P2 is equal to F2 divided by A2, pressure at area A2. F1 over A1 is equal to F2 over A2. Application of Pascal's principle. And that's it for now. In the next video, we'll continue our discussion on fluid motion. In the next video, we'll take a look at the concept of Archimedes' principle. So once again, that's it for now. Thank you for watching.